Welcome to Biogas Basics. My name is Jürgen Kuber, and in this presentation, I will talk about the heat balance of a biogas digester. I have come across many heat balances of AD plants, but almost all of them lacked one or more terms in the heat balance. Let's dive straight in. This is a stylized biogas reactor. It has a feed and dilution inflow and an effluent and biogas outflow. The digester is mixed by agitators or with gas or hydraulic mixing. The heat balance covers all energy terms: enthalpy flows, heat flows, and mechanical energy dissipation. The inlet and outlet mass flows are enthalpy flows. Mixing energy dissipates in the digester and will ultimately be converted to heat. The digester is heated and it loses heat to the environment. The last term is the heat of reaction. Like any other reaction, the formation of biogas and biomass from substrate and water has a heat of reaction. The total heat balance looks like this. I abbreviated the terms to the initial letters. Enthalpy streams are the product of mass flow, m dot, heat capacity, Cp, and temperature difference to a reference temperature, T minus Tref. We can choose the reference temperature to 0 degrees Celsius, which simplifies the formula a bit. The heat capacity of water is around 1.16 kWh per Kelvin and ton. For dry matter, it is roughly 0.5 kWh per Kelvin and ton. The enthalpy stream of all liquid streams is the sum of the enthalpy stream of water and dry matter for the respective stream. For biogas, it looks a bit different. Here, we need to take the heat of evaporation into account. When it leaves the digester, biogas is saturated with water vapor. The evaporation of water will cool the digester. The enthalpy is the mass flow of the dry biogas times its heat capacity, times the temperature, plus the water loading X, times the sensible heat term, heat capacity of water vapor, times temperature, plus the latent heat term, heat of evaporation. The water loading is the mass of water vapor per mass of dry biogas. It is the molar mass of water divided by the molar mass of the dry biogas, times saturation pressure over absolute pressure minus saturation pressure. We can fit the temperature dependence of the saturation pressure with the Antoine equation over the required temperature range. Vapor pressure data can be obtained from the NIST webbook. Mixing energy will be converted to heat eventually. Imagine an adiabatic tank with a mixer. After the mixer stops, friction will slow down the flow in the tank. Eventually, the flow will stop and all the kinetic energy of the fluid has been converted to heat. Mixing energy is quite easy to measure. Simply count the number of mixes and measure their power uptake and operation time. Use only active power, not reactive or apparent power. Alternatively, look at the motor sizes and assume a 50% load factor. If you make a heat balance in the design phase of the plant, you can use volume dissipated power to assess the heat dissipation from mixes. Digesters are typically mixed with 2 to 7 watt per cubic meter, depending on the viscosity of the digester and whether solid feedstocks must be mixed into the digestate. Assume a volume dissipated power and then multiply with the digester volume. If you use gas or hydraulic mixing, the approach is similar. For hydraulic mixing, calculate the kinetic energy of the flow exiting the nozzle. For gas mixing, take the enthalpy into account. Gas mixing will convert a substantial amount of the compressor energy straight to heat and not into kinetic energy. I will do a mixing presentation, where I will talk about this in more detail. The heat of reaction is often overlooked, but it is a significant contributor to the heat balance. As a rule of thumb, the heat of reaction is around 3 to 7% of the upper calorific value of the produced methane. The overall reaction is substrate plus water reacts to biogas and biomass. Typically, the reaction is exotherm. There are also terms for the solubilization and dissociation of CO2, and ammonium and bicarbonate, carbonate and ammonia. Calculate the heat of reaction with Hess's law from heats of formation. I go through this in my presentation about the stoichiometry of the biogas process. The digester loses heat over the ceiling, the wall, and into the ground. The general form of the heat loss equation is Q dot is the product of overall heat transfer coefficient U and heat transfer area A times temperature spread delta T. For straight walls and round walls with large diameters, the overall heat transfer coefficient is 1 over 1 over the heat transfer coefficient on the inner side of the tank, alpha I, plus thickness of the wall, delta W, over the thermal conductivity of the wall, plus the thickness of the insulation over the thermal conductivity of the insulation, plus 1 over the heat transfer coefficient on the outside of the wall. The thermal conductivity of concrete, mild steel, and stainless steel is typically 1.5, 20, and 40 watt per meter and Kelvin. The heat transfer coefficient between solid and gas is 20 to 30 watt per square meter at Kelvin for natural convection. The heat transfer between a liquid and a solid for forced convection is higher, typically in the range of 100 to 500 watts per square meter and Kelvin, depending on the velocity and viscosity of the fluid. Double membrane gas domes have an air cushion between the biogas space and the ambient air that insulates the digester somewhat. The overall heat transfer coefficient is around 2.5 watts per square meter and Kelvin. Now simply go around the tank and identify surface areas and whether the heat transfer is between a gas and solid or a liquid and a solid, and calculate the heat loss into the environment. The heat loss into the ground is the most difficult to determine. It can also fluctuate a lot from site to site. D plants with the same digester geometry and the same diet in the same area show different heat balances. Some digesters require year-round heating, most need cooling in summer, and some must be cooled the whole year around. The difference is caused by the different soil conditions. Areas with dry soil show the lowest heat loss into the ground. If the groundwater table is only a few meters below the digester baseplate, the digester can require continuous heating, even in summer. There is an analytical solution for heat loss into the ground, but it is a platonic trap. Here is the formula. R is the tank radius. K is the heat conductivity of the soil. Alpha is the heat transfer coefficient at the soil-air surface. Tf is the digester temperature. T infinity is the ambient temperature. The Bio number is a dimensionless number, similar to the Nusselt number, but for semi-infinite heat conductivity problems. It is alpha times characteristic length, the tank radius, divided by heat conductivity. The formula looks nice and neat, but it relies on some restrictive assumptions. The circular tank sits in an infinite empty plane and the soil heat conductivity is constant. At Z equals 0 and R smaller than the tank radius, the temperature is the digester temperature. There are two extreme cases which simplify the equation. If the Bio number is 0, the heat conductivity resistance is much higher than the heat transfer through the soil. The isotherms are vertical at the surface. The heat loss is 4 times heat conductivity times tank radius times temperature difference between tank and environment. This formula underestimates the reality significantly. In the second extreme scenario, the Bio number goes to infinity. The resistance of the heat transfer through the soil is small compared to the heat transfer on the surface. The formula is 2 pi alpha r squared times temperature difference. Again, it is purely academic, but its form is interesting. It is very similar to a convective heat loss term. The area times twice the heat transfer coefficient times the temperature spread. When calculating the heat balance, I use the two extreme cases of heat loss into the soil and take the least favorable. If the digester is in danger of overheating, I use a minimal heat transfer coefficient into the ground, which will lead to a higher cooling demand. If the digester requires constant heating, I assume a high heat loss term to ensure that the heating is sufficiently sized. Do not use the formula that relies purely on soil conductivity. Heat loss into the ground can be modeled with a heat transfer coefficient of around 5 watt per square meter and Kelvin to an average soil temperature. The average soil temperature is the average ambient temperature at the respective location. So, if the temperature varies between 0 and 20 degrees Celsius, the soil temperature is 10 degrees Celsius. Now let's put it all together. We can rearrange the heat balance for the heating term. This is the heat required to keep the digester temperature stable. What happens if we switch off the heating? In this case, the digester starts to cool down. The heating term is replaced with the product of digester heat capacity, digester mass, and the rate of temperature change dt over dt. This form of the heat balance can be very helpful to assess additional heating or cooling demand of real digesters. If a digester slowly overheats or cools out, we can determine the additional cooling or heating demand by measuring the temperature gradient and multiplying it with the digester heat capacity and mass. If a 3,000-ton digester with a heat capacity of 1 kilowatt-hour per ton and Kelvin cools out by 0.5 degrees Celsius per day, the additional heat requirement is 3,000 times 1 times 0.5 divided by 24 hours per day, which is 62.5 kilowatts. We do not need to know all terms in the heat balance to calculate the incremental heating demand. Let's calculate an example. We have a single digester with an internal diameter of 22 meters, a height of 8 meters, and a volume of 3,041 cubic meters. The tank wall is 20 centimeters concrete and 8 centimeters insulation. The tank has an insulated concrete roof and base plate. The digester is fed with 110 tons per day. The feedstock has a yield of 200 cubic meters per ton. The biogas has 52% methane. Further, the digester must be diluted with 20 tons per day of processed water, which has 34 degrees Celsius. The total inflow are 130 tons per day or 5.4 tons per hour. The digester makes 917 cubic meter biogas per hour, which are 1.26 tons per hour. The resulting effluent is 4.2 tons per hour. The digester temperature is 40 degrees Celsius. The volume dissipated power from the mixes is 6.6 watts per cubic meter. In the winter scenario, the ambient temperature is 0 degrees Celsius and the feedstock has 4 degrees Celsius. The enthalpy of the inflow is 54 kilowatts, the effluent outflow is 193 kilowatts, and the biogas outflow is 56 kilowatts. The mixing energy is 20 kilowatts, the heat of reaction is 184 kilowatts. The total heat loss is 52 kilowatts, 4 kilowatts go into the ground, 9 kilowatts leave over the wall, and 38 kilowatts leave over the roof. We can tally up the heat balance. The heat demand of the digester is 43 kilowatts. This amount of heat is required to keep the digester temperature unchanged. Without heating, the digester will lose 0.26 degrees Celsius per day. Now let's change to the summer scenario. The feedstock and ambient temperature increase to 20 degrees Celsius. Most terms in the heat balance stay constant. The changes are the enthalpy of the incoming feed stream and the heat loss term. The enthalpy of the incoming feed stream increases to 139 kilowatts. The total heat loss drops to 28 kilowatts, 4 kilowatts go into the ground, 5 kilowatts leave over the wall, and 19 kilowatts leave over the roof. The gap in the heat balance is minus 65 kilowatts, expressed as heating. So, in the summer scenario, the digester required 65 kilowatts cooling. Without cooling, the digester temperature will rise by 0.39 Kelvin per day. Let's summarize. The heat balance of a biogas plant comprises the enthalpy flows of the incoming and outgoing liquid streams, expressed as mass flow times heat capacity times temperature. The enthalpy stream of the outgoing biogas flow must be extended by the heat of evaporation. The biogas leaves the digester in saturated form, and the evaporating water cools the digester. The energy input of the digester mixes must be considered in the heat balance. Use only the active power of the mixes. The mixing energy heats up the digester. The heat of reaction can be a large term contributing to the digester heating. The exact heat of reaction can be calculated from the stoichiometry of the biogas process, which must include the biomass formation. The heat loss cools the digester. Heat loss over roof and wall can be calculated with literature approaches, but the heat loss into the ground is difficult to quantify accurately. Both best and worst case scenarios must be considered. The term that completes the heat balance is the digester heating, i.e. the amount of heat that must be added to the digester to keep the temperature stable. The term can become negative, which means the digester must be cool. If the digester is not heated or cooled, the heat balance can be used to predict the rate of change of the digester temperature. This concludes the heat balance presentation. Drawing the heat balance around a biogas digester is not difficult, but it is important that all terms are considered. I hope you have learned something new, and I see you in the next episode of Biogas Basics.